Hello there. My name is... You may remember me from Who Wants to Be a Millionaire?
C. Final answer.
That one episode from The Office and a couple of short videos I posted. See, I was working on some audio builds. Then remembered, you guys don't even know how to read schematics yet. Don't worry, that's what I'm here for. Because I took time off my real busy schedule in order to bring you this introductory guide to audio schematics, patent pending, where you will learn how to read audio schematics. You will like it. But first, a word from our sponsor, fractalmusic.com. That's my website, bozo. In fractalmusic.com, you'll find guides, schematics, and even hot singles in your area. Visit fractalmusic.com and get access to all of this for the low price of free. That's right, folks. For a limited time only, you can get access to all of the content in fractalmusic.com for free. No ads, no subscriptions, no shady executable downloads for now. So what are you waiting for? Visit fractalmusic.com today and start doing something with your life. Back to the video. I know, I told you you'd learn how to read schematics and now I'm getting into mathematics and stuff, but this is important. Back when you were young, you probably learned about this formula called Ohm's law. It looks a little bit like this. Voltage equals resistance times current. And while it may not look like it, this is the perfect way to start introducing the remaining concepts for this video. So, let's break it down. This is defined as the electric potential between 2 points in a circuit, and that just means nothing to me. So, here's an analogy. Imagine you're rolling a boulder up a hill and let it sit there at the top. Now, that boulder has some potential energy. It's just waiting for a little push to turn that potential into something useful. And that's kinda what's going on with that electric potential mentioned before. Voltage being that possibility of power flowing through a circuit. So, in this battery, the positive terminal is like the top of that hill, and the negative is the bottom, or what we usually call ground. Through this, you can make anything be the ground, and even have negative voltages. So that boulder is kinda like a... You can think about it as the actual movement of those electrons trying to go from A to B. So that's when our boulder finally rolls down and starts doing something with its potential. Only it's not really the electrons moving, it's more like...
rate at which they move.
It's a mess. So just check out any of the channels down below if you want to learn more. So, with that out of the way, we can get to... The electrical resistance is a property that tells us just how difficult it is for those electrons to move from point A to point B. So, if we have a low resistance, it's really easy for those electrons to move around, and a high resistance means it's much more difficult. So, if a low resistance is like our heel being real smooth and having little friction, then this is what a high resistance looks like. It's all uneven and ugly, and some idiot placed a speed bump there for some reason. The boulder now starts having a difficult time going down. It decelerates, and all that potential energy is being spent on getting over the obstacles, instead of making big rock go fast. And now, we can actually pivot into some schematics, because unlike voltage or current, we actually have a component that we can take a look at.
Hundreds of resistors waiting for your call right now. Buff
resistors,
classic
resistors,
mystery
resistors.
So these are resistors. As you saw previously, these come in many shapes and sizes. Bigger ones tend to have a higher power rating, meaning they can withstand more heat before getting toasty. There's also variable resistors, called potentiometers, but don't worry too much about those right now, because we'll focus on these super common THT low-power resistors, the kind you'll find everywhere. See those markings?
Yeah.
These tell you the resistance of any given resistor. Just look it up on this chart, or use a multimeter to check the value. In a schematic, resistors are represented with this symbol, a squiggly line that makes our electrons zigzag around, making it harder to get to the other side. Or as this boring box full of nothing, if you care about international standards. It's super easy to map these to the real thing, as they aren't polarized and thus the orientation you place them in a circuit doesn't matter. But the same cannot be said for... These are electrolytic capacitors. And if you've ever seen an electroboom video before, you know these care a whole lot about how you place them. That's because these are polarized. So in schematics, we draw them like this, with a little plus sign to let us know how to place them in a circuit, or else, you know. But okay, not all capacitors are the same. There are some more progressive ones, such as film, ceramics, and polyesters. These are all non-polarized, and to draw them, we do so like this. Fun fact, those expensive condenser mics you love so much are actually just capacitors. In a circuit, capacitors will seem to act a bit differently depending on if you place them in series or in parallel. When placed in series, you can think of caps as little barricades that stop the rocks from going down entirely. While, in parallel, it's like this little reservoir that gives you a constant stream of rocks. At least that's one overly simplified way to think about it, and it kinda holds up until you get to... See that hill we've been using? Right now, voltors can only go down in a single direction, and that's similar to what's going on with DC. Electrons moving continuously in the one direction. But there's also AC, or alternating current, where things get a little weird. Imagine that same slope, but now it's doing this, constantly alternating its highest and lowest points, meaning that the potential energy is oscillating back and forth with a certain rhythm, or frequency. If we plot it over time, we get something like this, known as a sine wave. But AC presents itself in a lot of different ways, some common ones being also squares and triangles. It can also take the form of super complex waveforms, and it's still going to be called AC, as long as we're oscillating from a set reference point. In most cases, that's ground. To summarize, voltage sources can either be AC or DC. In audio electronics, DC is most likely gonna be our power supply, while AC is gonna represent our inputs and outputs. For example, a guitar's pickups, a microphone's signal, even a function generator when dealing with synths, and they can be represented in our schematics with all of these symbols. I previously mentioned that caps behave differently when placed in series or parallel. Or do they? First, let's talk a bit about schematics. These show the components required for a given design and how they should be connected to one another. That's determined by these lines that represent the conductors. More often than not, that's wire. But let's start simple. This is how most circuits behave. We have a power supply connected to a load represented by this resistor. In this simple model, the resistor is both series and parallel to our supply. So let's fix that. Now we have two resistors instead of one. In this configuration, these two resistors are in series, as they are connected through a single node. It's as if our rocks had to go through two hills back to back. As we go down, our electric potential gets depleted, but the same number of rocks is preserved along the way. That's because current is preserved through the components in a series connection, but the voltage drops with each load. Then, what is a parallel connection? Let's get back to our model and move things around. The two resistors are now in parallel. So, our supply now meets the two at the same time, right at this junction. It's as if the rocks had to face a decision and can't take a second route. Some of the rocks head down the usual way, but others take the new route. Now, we have a different number of rocks in path A and path B, but we have the same potential in either route. That's because, in parallel connections, voltage is preserved, while current gets split through each load. As mentioned before, our components will behave differently when connected in series or parallel. For example, resistors in parallel will have a lower total resistance. This value is determined by this formula. And when we connect a bunch of series resistors, we can reach one chunk of resistor. Caps are the opposite. Series gives us a lower capacitance, and parallel gives us a larger one. Okay, so let's take a look at how we could actually build a circuit from a schematic. Today we'll be building this guy right here. This is a simple passive bandpass filter, which just consists of a couple of components. You may also find schematics being drawn this way, which use net labels instead, but today we'll stick to the basics. Okay, so let's take a look at what we need. A trusty old breadboard, a bunch of jumper wires, our resistors, and a whole lot of caps. So, right off the bat, we do have a problem. See, we need a 1.5 nanofarad cap right here, but if we take a look through our collection, we don't have any. We do have, however, 1 nanofarad, 300 pico, and 200 pico, these two being 0.3 nano and 0.2 nano respectively. So we can take a couple of approaches. We can take these three caps, connect them in parallel, and get something akin to the 1.5 that we need, or we can use three 1 nanofarad caps in this configuration. I'm just gonna do this one. Okay, so here we have our 1.5 nanofarad cap connected to our input, which is this yellow jumper right here. From here I'll connect a 100k resistor to ground like so. And now my second resistor from the same terminal. Cool, from here now I just have to connect my last cap to ground. Now I'll just connect some jumpers. And the circuit is done. Here, my blue jumper is my output, and the black one is my ground. Now let's take it for a spin. Okay, so here's our guy, and
We go to the oscilloscope. We get a sine wave, an 800 hertz sine wave. But as we go down, and down we go, we see how the amplitude gets dropped by a fair bit.
Epilogue.
Okay, so hopefully this can serve you as a starting point when getting into audio electronics. While it may seem daunting at first, it does get easier. And look, I'm a bit of an idiot myself, and even I can read a couple schematics here and there. So, what's stopping you? If you're eager to start building some stuff, you can get one of those cheap Arduino starter kits, and then you can look up schematics in a book, online, or you can always visit fractalmusic.com if you want to take a look at a couple of my designs. There's also my short videos if you want to watch those. But anyways, thank you so much for watching. In the meantime, you can always subscribe, like the video, and tell me what you want to see next. Okay, love you, bye.